Okay, on the last video, we talked about the 6 trig functions, and I showed you how to evaluate the 6 trig functions using a calculator. For most angles, you would need a calculator in order to evaluate the sine, cosine, or tangent of whatever angle we have. But there are certain angles that we can use some geometry to be able to figure out what the sine or cosine or tangent is of an angle without using a calculator. And these are referred to as the special angles. And so there's 3 of them in particular. The first one we'll start with, I did this on the previous video, but if you had a perfect square, and in the world of rectangles, right, squares are pretty common and important. If I took a square and cut it diagonally and just use the bottom half here, for example, to create a triangle, then we can call this angle theta. And let's use numbers here. So if we had a square here, let's say that this side was 1 and this side was 1. If we do a Pythagorean theorem to figure out what this hypotenuse is, we'll call this 1, this is 1. We can always go 1 squared plus 1 squared equals the hypotenuse squared. That's 2 equals h squared. So h would be the square root of 2. And see, now we have all 3 sides of this triangle. And so if I want to find the sine, cosine, or tangent of, now what would this angle be? I forgot to mention. If this was originally 90, then this angle, when I cut a diagonal, would bisect it. It would be 45 degrees. In radians, 45 degrees is pi divided by 4. Remember how you can convert that. Might as well practice that. 45 degrees, my conversion is, if I multiply by pi over 180, 45 ends up going into 184 times, so that is pi over 4. Mostly I'm going to work in radians because I want, since this is pre-calculus, when you get to calculus, as I mentioned before, most of the time we're going to be working in radians. So from this triangle, I can now find the sine of pi over 4, the cosine of pi over 4, the tangent of pi over 4, and of course, once I have those, I can do the reciprocal functions. Using our definitions, remember sine is opposite over hypotenuse. This would be the adjacent side. So the sine of theta would be 1 over root 2. I also mentioned before that nobody cares when you get to calculus if you leave a square root in the denominator. So 1 over root 2 is perfectly fine. That being said, because these special angles are so commonly used, you need to be prepared to also see the sine of pi over 4 written as, if I were to rationalize this by multiplying by root 2 over 2, root 2, that comes out to be root 2 over 2. So either one is fine. 1 over root 2 or root 2 over 2, they're the same. And I think it's important to know both of those because there's times I prefer to use this and there's times I prefer to use this. For example, the reciprocal of sine is cosecant of theta. That's the reciprocal of sine. So I can take the reciprocal of either one of these values. If I take the reciprocal of that, I'm going to have another square root in the denominator. It's going to look kind of ugly. But taking the reciprocal of this is a lot easier. The reciprocal of 1 over root 2 is just root 2 over 1, which is just root 2. Okay. Cosine of pi over 4. Cosine is the ratio of adjacent over hypotenuse. So that is also 1 over root 2, or as we saw, that could be written as root 2 over, not root 2 over root 2, root 2 over 2, sorry. Let's start over, root 2 over 2. So I could also figure out that the secant is the reciprocal. I'll just take the reciprocal of that again. The secant of pi over 4 is also root 2. Tangent of pi over 4 is the ratio of opposite over adjacent. That's 1 over 1, which is just 1. So that means the cotangent of theta, the reciprocal of 1, is still 1. We don't work with the reciprocals that much. And certainly you'll agree, if you can get these 3 down, if you can get the sine, cosine, and tangent of pi over 4 down, and you know which reciprocal goes with which function, you can always figure these out. So what it really boils down to is knowing how to find the sine, cosine, and tangent, in this case of pi over 4. And you can get that from the triangle. Now there's two more special angles that have to do with triangles. And for these two, they come from another very familiar and common shape. So here I've drawn a triangle. And specifically what I was trying to draw was an equilateral triangle here. Remember, an equilateral triangle, all sides are the same. And if all sides are the same and the sum of the angles have to add up to 180 degrees, that makes each angle 60 degrees. If I bisect this triangle by dropping an altitude down and just working with this part right here to get a right angle, then I could get this right triangle where this is 60 degrees. 60 degrees in radians is pi. Always remember pi is 180. So the way I do it quickly is, what would I divide 180 by to get to 60 degrees? I would just divide it by 3. Now, if I bisect this angle, this is going to turn into 30 degrees. And 30 degrees is 180 divided by 6. 30 degrees is the same as pi over 6. For this problem, it's actually easier if I started with, because I'm going to bisect here, if I start with each side being 2 before I bisected this, that means if I drop this altitude down, this is going to now be 1. So I have this being 2, maybe I'll stick with blue. This is 2, this is 1, and I can figure out this side right here by using the Pythagorean theorem again. Be careful. The missing side is one of the legs, so it would actually be 1 squared plus, let's say, x squared equals 2 squared. That's 4. If I subtract the 1, I get 3. So this other side here would be the square root of 3. So from this triangle, I can actually learn the sine, cosine, and tangent for 2 more angles here. One of them is pi over 3. Let's do that. Sine of pi over 3, cosine of pi over 3, tangent of pi over 3. From pi over 3, root 3 is the opposite side, 2 is the hypotenuse, and 1 is the adjacent side. Sine of pi over 3, opposite over adjacent gives me the square root of 3 over 2. Cosine, adjacent over hypotenuse gives me 1 over 2. And tangent is opposite over adjacent, the square root of 3 divided by 1, which is just square root of 3. Now, of course, I know you could get the reciprocal functions once you know those 3, so we'll skip those. But what I can also do is I have another angle over here that I could also find the sine, cosine, and tangent of, pi over 6. The only thing I have to do now is I have to change my perspective. If I was at pi over 6, this angle here, the side that is now opposite me is now the 1. So I'm going to change this to opposite. And this root 3 is is an adjacent side. If I'm working with pi over 6, the hypotenuse is always opposite the right angle, so that's not going to change. Sine of pi over 6 now is opposite over hypotenuse, 1/2. Cosine is adjacent over hypotenuse, root 3 over 2. And the tangent is opposite over adjacent from this angle, 1 over root 3. Again, you can rationalize if you want. You don't have to. You rationalize by multiplying by root 3 over root 3. You end up with root 3 over 3. So here are 6 more. So the deal is this: you no longer need a calculator. If the sine of pi over 3 comes up on a trig problem in pre-calculus, you're supposed to be able to figure out that the sine of pi over 3 is root 3 over 2 without using a calculator. Okay. Same thing with pi over 6 and pi over 4. Now, here's my view on this. You can either memorize these if you want to, but you'd have to agree that if you could get this triangle down, if you know how to reconstruct this triangle, and remember how I did it, starting with an equilateral triangle, And getting these sides and knowing hypotenuse, adjacent, opposite, there's no reason to memorize these. You can just use the definitions. Same thing for pi over 4. If you can just remember how to reconstruct that triangle using your definitions of sine, cosine, and tangent, you don't need to memorize all of these, right? You just need to know these. So I'm a bigger fan of just knowing how to construct those triangles. That's the key to everything going forward here, to a lot of stuff. Now, there are some other angles that you are expected to know how to find the sine, cosine, and tangent of, but they don't really involve triangles. And those angles would be an angle. So now I'm going back to my triangles being on the circle that we talked about, because that forms an angle here. But in particular, what I'm going to try to do is, what if I have an angle of 0 degrees or 0 radians, 90 degrees, which is pi over 2, or 180 degrees, which is pi. Remember, this was 3 pi over 2, and 0, I'm going to call that 0 radians, is the same as 2 pi. See, if I have an angle of 0 degrees, I can't make a triangle. Same thing at pi over 2. I can't make a triangle that's inscribed inside this circle. So it's a bit tricky. So what I'm going to do to figure those out is I'm going to use what we call the unit circle. The unit circle just means, this term unit just means that the radius is 1 unit. And if the minute I wrote unit circle, I'm going to bet many of you said, oh no, here it comes. If many of you took trig before, you probably have this awful memory of a unit circle, which is a circle like this with all kinds of angles and coordinates around the circle that you were taught to memorize. I'm not big on that, okay? I'm only using the unit circle here for a specific purpose. And after that, I'm not going to really need the unit circle after I teach you something else. What I always tell students, however, is if a little refreshing of the unit circle that you learned before works, and you can figure out the sine, cosine, and tangent of special angles just from memory, without referring to your unit circle, I'm not out to change you. But what I also have recognized is that many students have learned it. They could do it when they were a junior in high school, and then they have completely forgotten it. And it's, what good is something if you're going to forget it every single time, right? So I'm just trying to give you different tools so that you could recall and get yourself through trig problems as you move through calculus and beyond. Okay, so I don't use the unit circle other than for this particular purpose here. Okay, so say I have an angle here, and now since it is on the xy axes, notice that this distance is x, right? That's how we could locate points, and then I would go up y. So this point literally is xy over x up y. And the radius of our circle, which would be the hypotenuse of our triangle, is 1. If I now use my definitions, so if I said, what's the sine of theta in terms of x, y, and 1, the sine is opposite over hypotenuse, y over 1, which is just y. The cosine is adjacent over hypotenuse, x over 1, which is just x, and the tangent of theta is y over x. So what we learn from this is, if you're talking about a unit circle, then an xy is a random point on this circle. The sine of your angle, whatever angle on, is literally just the y coordinate of that point. And the cosine is literally just the x coordinate. And the tangent is the y coordinate over the x coordinate. Or I guess you could think of it this way. If sine is y and cosine is x, then that means tangent of theta can also be thought of as the sine of the angle divided by the cosine of the angle. This is the first of what we call a trig identity. An identity in trig is just an equation that just happens to be true. It is true that for any angle, the tangent of the angle is the same as the sine of the angle over the cosine of the angle. Okay, but back to this. So how does that help me? We talked about how 0 and pi over 2 and pi, it would be tough to find the sine and cosine because you can't make a triangle out of it. You have no substance to it. But now that I know the relationship between sine and cosine and the coordinate on a unit circle, what I could do is on a unit circle, think about the coordinate of this point, which would be 1, 0. And so what that would then tell me is the sine of 0, 0 radians or degrees. Sine is literally the y coordinate. So because the coordinate at 0 is 1, 0, the sine of 0 is 0. The cosine of 0 is the x coordinate, which is just 1. And I could even do, since I've talked about it, the tangent of 0. Tangent is sine over cosine, so that's 0 over 1, which is 0. What if I wanted to do pi over 2? If I wanted to find the sine of pi over 2, I got to think on the unit circle up here at pi over 2, what would be the coordinate of this point? Well, it's a unit circle, so the x coordinate would be 0, the y coordinate would be 1, 0, 1. Sine of pi over 2 is literally the y coordinate, so it would just be 1. Cosine of pi over 2, literally the x coordinate is 0. And I'm running out of room here, so I'll go over here. The tangent of pi over 2 is the sine over the cosine. It's 1 over 0, which is actually undefined. There are some angles where tangent is actually not even defined. You're dividing by 0. Take a minute to pause the video and see if you can find the sine and cosine and tangent of pi and 3 pi over 2. Okay, if you're going to do pi, so I'm going to have to move this over. So if you're doing pi, just reconstruct this. What you'd want to think about is on your unit circle, pi is right here. The coordinate, what would be the coordinate on a unit circle here? My x value would be -1, my y value would be 0. So the sine of pi is the y value is 0. Cosine of pi is the x value, it's -1. Tangent of pi is sine over cosine is 0. If I wanted to do 3 pi over 2, I'll just go a little further down here on the unit circle. This point here would be 0, -1. This is y. So the sine of 3 pi over 2 is the y value, -1. Cosine is 0. Tangent, -1 over 0, which is another time where tangent is undefined. All right, so this sort of concludes any angle now that is a special angle. In other words, has something to do with an angle of either pi over 4, pi over 3, or pi over 6. You're responsible for knowing how to find the sine, cosine, and tangent without a calculator. Or, okay, another way to summarize these types of angles that we've done is any angle that puts you right on the x or y axis. You need to know how to find the sine, cosine, and tangent of that angle. And now this is how one way you can do it is by thinking about the coordinate on the unit circle that corresponds to that angle. And very soon, as I said, I can show you another way to find the sine, cosine, and tangent of angles that put you on the x or y axes without using the unit circle, and we can just ditch the unit circle altogether. But that's coming up later. All right.